I'd like to introduce Dr. Guy Blelloch. Good afternoon and welcome. It's my pleasure to introduce our speaker today, Dr. Guy Blelloch. I detect some Scottish in that heritage, that name. He's the Associate Dean for Undergraduate Education at Carnegie Mellon School of Computer Science. Dr. Blelloch received his BA and BS in Physics and Engineering from Swarthmore College and his PhD in Computer Science from MIT in 1988. He joined the faculty of Carnegie Mellon in 1988, where he teaches algorithms and parallel processing. Dr. Blelloch is one of the world's preeminent researchers in the area of programming languages and algorithms and how they interact, with an emphasis on parallel computation. He worked on one of the early parallel machines, the Thinking Machines Connection Machine, where he developed several of the parallel primitives. At Carnegie Mellon, Blelloch designed and implemented the parallel programming language NESL, N-E-S-L, a language designed for easily expressing parallel algorithms. Other work on parallelism has addressed issues in scheduling, algorithm design, cache efficiency, garbage collection, and synchronization of primitives. Dr. Blelloch serves as the co-director of CMU's Aladdin Center, which was established in 2001 for the study of algorithms and their applications. It is funded through the NSF ITR program and is a collaboration among several departments at Carnegie Mellon, as well as industrial partners and Princeton University. So please join me in welcoming this educator, researcher, and pioneer in the field of parallel algorithms, Dr. Guy Blelloch.
Okay, so today I'm going to be talking about parallelism, and this talk actually comes both out of research I do and teaching I do, as well as curriculum development. And in fact, some of the stuff I'll talk about now was influential in our design of some of our intro curriculum for the Pittsburgh campus, which of course is used here as well, including the design of the course 210, which is taught here. Okay, so parallel algorithms come of age. So let's talk a little bit about algorithms, first of all. What is an algorithm? I had to go to Merriam-Webster to figure the definition, since I couldn't really figure it out on my own. Apparently, it's a procedure for solving a mathematical problem by some sequence of steps. Of course, we all basically know what an algorithm is. Algorithms have a nice long history. Okay, they date back. I'm sure people thought of some forms of algorithms even earlier, but early work by Aristophanes on methods for finding the primes. So this was a systematic way to go through and enumerate the primes. And of course, the name algorithm itself came from Muhammad al-Khwarizmi, in the around 800 AD, when he invented methods for solving first, linear and quadratic equations, as well as for basic arithmetic in the decimal system. And of course, the decimal system at the time wasn't the popular system. It was the Roman numerals, at least further east of here. So, that's the old time. And then Gauss, in the 1800s, invented what we now call the fast Fourier transform, which is a way to do Fourier transforms in n log n steps instead of n squared. And then there were algorithms for various graph problems, including the minimum spanning tree in 1926. Of course, this all predates computers. So these were algorithms which were computed by humans, not by computers. But they were algorithms. They were systematic methods to calculate something. So it was a rule, and a lot of them involved loops. So certainly the arithmetic algorithms by al-Khwarizmi involved, iteration over the digits of a number. And so they were the basic idea of algorithms done by humans instead of computers. And then, of course, in 1935 and 37, Church and Turing came up with the hypothesis that both the lambda calculus and the Turing machines were equivalent universal machines for computing, and with them you could solve any algorithm on a computer as opposed by humans. So that's the early history of algorithms. And then there's sort of what we might call the modern history of algorithms, and this is the sort of algorithms we teach in our courses. And they date back to Dijkstra's famous algorithm in the mid-50s, quicksort in the 59. These algorithms we teach all of our undergraduates at this point. Then the invention of complexity theory, the notion of, Knuth wrote his original books on algorithms in the late 60s. NP completeness, that idea came in 71. Some people are surprised that that idea came after Knuth's volumes, after the discovery of a lot of these other algorithms. Big O notation came after Knuth's books. If you go look at Knuth's books, they do not use Big O notation, at least his original books. He has some revised versions that do. And then there was sort of this design analysis. It was the first algorithms textbook. Okay, it happens to be the textbook I learned from when I was in graduate school. I'm of the age where pre-Corman-Lises from Revest, which is now the common textbook, that's what everyone learned for. So when I was studying at MIT in graduate school, that was the textbook to learn algorithms from. Now, in all of these algorithms, the costs were measured. And in algorithms, you care about not just computing something, but you care about that you compute it reasonably efficiently. And so when you talk about efficiency, we talk about the number of computing steps taken by some sort of machine. Okay, so that's what's called a sequential steps. Nowadays, algorithms taught in every curriculum, probably in the world, in computer science. I doubt there's a single curriculum out there in computer science that doesn't have an algorithms course. Most curriculum actually have 2 courses with algorithms in the title, in their requirements. So certainly at CMU, we have 210 and 451. If you look at the actual name of the courses, they both have algorithms appearing in the name. Okay, and they're both required by every single one of our students. There's only, I guess, 7 courses which are in CS which are required by all of the students. And beyond these 2 courses, of course, there's many other courses which do a little bit of algorithms. Some of our programming courses cover some algorithms, and some of our AI courses, etc. And this is not just true at CMU. MIT has 2 required courses which have algorithms in their name. Berkeley has, one's got an algorithms, the other's got data structures, which is sort of the same as an algorithm. Stanford, being a much weaker program, only has one course called algorithms. But they have this track system that you get to decide if you're going to get focus on more the theoretical side or not. And if you focus on the theoretical side, then indeed you have to take another algorithms course. The point being is that algorithms are prevalent in computer science. And of course, algorithms are not just an educational thing. They're used in the real world. Okay, and that's part of the reason. So here's The Guardian from, I guess, a couple years ago, basically claiming that algorithms rule the world. I'm not sure if they meant this in a particularly good way, given that NSA appears next. But algorithms are used all over in all sorts of cool applications. Most of what I'm taking here are just news articles from the last year. So here's how algorithms are used for revolutionized drug discovery, new algorithm for drug discovery. And here's an article from Trends in Tech that say the future emphasis should be in algorithms and not code. So they're claiming there should be more focus on algorithms and less on coding. Here's some Harvard running a thing that basically saying, in their business school, that's saying algorithms is, the economy of algorithms, computational economy, using algorithms to, analyze economy, et cetera. Algorithms are used for all sorts of weird things. You can predict gentrification, apparently, using algorithms. Okay, so if you want to know if your neighborhood's going to get gentrified or not, you can pick up the right algorithm. Courthouses, so even in law, algorithms are being used to, give advice. Basically, courtrooms are turning to algorithms for advice. Okay, and in fact, if you watch on popular TV, there's various shows about how lawyers are now using algorithms to predict what people are going to think and say. They're even used to design chairs. Okay, so the chair you design sitting on might be designed by an algorithm. And in this side of the world, this might be relevant. Okay, algorithms are used to optimize oil wells, presumably also gas wells or gas, whatever they are called. They're not always good. Okay, algorithms are sometimes bad. So apparently they cause the flash crash. We can blame that on algorithms as well. So they do, you can use algorithms as you will. Point being is algorithms, and these are just titles from articles. So, the algorithms are used in all sorts of interesting applications. So why are algorithms so successful? Well, they're a computational method. Now, when we teach algorithms in a course, we teach about, big O analysis, and we teach about performance and calculating all these mathematical ideas of how fast an algorithm runs. So you might say, well, the reason algorithms are successful is they predict, run times, exactly predict run times. I claim that's probably not true. Okay, algorithms are not particularly good at exactly predicting a runtime. Okay, that's probably not, we put a lot of emphasis on runtime when we teach them, but predicting runtime exactly, or they're good for highly tuning optimized code. So if you take an algorithms course like the two I mentioned from Carnegie Mellon, you're probably not learning actually how to optimize code, so that's probably not a reason algorithms are successful. To impress your friends, I guess that depends on who your friends are. Since most of our friends are computer scientists, yes, maybe you can impress your friends with the cool new algorithm you just learned. So that's a maybe. But there's actually a lot of definite yeses, why algorithms are so successful. They teach abstraction. Okay, the very first thing we teach in algorithms is the notion of an abstract data type, an abstract data structure. We talk about queues and stack. We talk about abstract problems like sorting as opposed to particular implementations of a sort. So there's a lot of how to think abstractly. There's also a lot about explaining core ideas and why they're useful. So it's a methodology of talking about, the core ideas that you need to solve a problem computationally. The cost models, I say, they're not going to predict your running time exactly, but what they do is they're quite simple, and they give you a good sense of when one algorithm is going to be better than another. So they tell us that quicksort is probably going to be better than insertion sort. They're not going to tell us the runtime of quicksort down to microseconds or of any accuracy at all, but they do give us a sense of why one is better than the next. And they also give us a nice way to write pseudocode. So most textbooks and algorithms, you describe them in some sort of high-level pseudocode. You don't have to worry about the details of a particular programming language. And that's a nice way to describe how the computation works without getting bogged down in details. And the last thing is that they're elegant. Algorithms, you get these very simple descriptions of interesting ways to solve problems. And so there's a lot of elegance in them. So these are, real reasons that they're useful as well as just being practical. So what about parallel algorithms? This talk is not about algorithms per se, it's about parallel algorithms. Well, parallel algorithms are really a subclass of algorithms. And I had to look this up. Merriam-Webster's didn't have a definition of parallel algorithms. So I had to go to the next best source, which was Wikipedia. And this is what I found at the top of Wikipedia. Apparently, well, you can read it, right? It's an algorithm which can be executed piece at a time on many different processing devices and then combined together at the end for a correct result. I'm not sure if this is exactly how I would have defined it, even though, as it turned out, and I didn't realize this until I went to the definition, this one is actually one of my papers. But somehow, I would have said something different. Because this makes it sound like you do everything separately and then you combine it at the end. In reality, you're working in a parallel algorithm. You're doing lots of things at the same time on different processes, but they're talking to each other all the time. So it's not that they're all working independently and then at the end they come together and agree on a solution. They're talking to each other. So it's like in this room, if you were trying to solve a problem, you could all go to your corner of the room and work on it independently and then come together. Or you could just discuss it among each others. And parallel algorithms are more of the discussion form, that you discuss it among each other and you come to a common solution. But it's the main difference of a parallel algorithm from what's traditionally called a sequential algorithm is there's lots of computing devices working at the same time, as opposed to just one step at a time. If you remember my Merriam-Webster's definition, it said step at a time. So certainly the Merriam-Webster definition was still thinking in terms of sequential algorithms instead of parallel algorithms. So of course parallel algorithms also have a history. There's some early algorithms, they're of course later than the sequential ones, but there's some early algorithms in the 70s. Then there were some models that were modeling how to cost. And then there's also some theory, just like the theory of NP completeness. There's a theory of parallel algorithms about what you can do efficiently in parallel. And that's what this NC algorithms are in the 80s. And just like in sequential algorithms, eventually someone wrote a textbook. And as it turns out, this is the textbook here. And if you read the letters down here, it says CMU QA 78. So this textbook was actually checked out of your library here. And just coincidentally, I was put in an office in the computer science hallway. And I looked up on the shelf, and there was this book on the shelf in my office. It had been checked out of the library and apparently never returned. So it's just sitting there on there. But this is a book on parallel algorithms from the late 90s, although it's not widely used. And part of the issues I'm going to say is parallel algorithms didn't really pick up at the time in 1990 in the same way that sequential algorithms did. And there's various reasons which I'll mention along the way. In fact, in the mid-90s, there was sort of a hibernation of parallel algorithms. People didn't focus on it. There were no courses on it beyond some graduate courses I might have taught on the topic and some other people. But why parallel algorithms now? So I claim that we really should be focusing on parallel algorithms now, and maybe the world hasn't come around to this yet. But there's several reasons, and I'm going to go through each of these in more detail. But the first is that nowadays you can't find a computer that's not parallel. Okay? Even the simplest devices, I think my title I said, all but a toaster. Even your washing machine probably has a parallel processor in it. And furthermore, all sorts of applications can make use of parallelism. In fact, do make use of parallelism. In fact, most of the algorithms I mentioned in that first list, a good chunk of them were actually parallel. So if you're going to do something like oil exploration, you're almost definitely doing it using parallel algorithms because you just need a lot of computational power. They have simple programming and cost models. I'll talk a little bit about this. There's efficient parallel algorithms for many different problems. So many of the problems that we normally think about solving sequentially, sorting or whatever it might be. And some of these things are reasonably new, that in the last 5 years there's been a big advancements in programming languages, tools, programming languages for parallelism. So it's a lot easier now than it might have been 10 years ago. And the other thing is many of the algorithms that we think of as sequential are really parallel, and you just have to turn your head a little bit to the side to realize that they're parallel. And I'll give some examples. So let me just go through some of these. So almost all computers and devices are parallel. Okay, so if you go to Amazon and search Intel processor, you might pop up some list of processors. I very much doubt you can find a processor that doesn't have multi-core. Okay, you probably can find some which only have 2 cores, or maybe this one will pop up. I think this is the first one that popped up for me. This one has 8 cores, $100. You can buy this 8-core processor, and so most machines you buy now, well, all machines you buy nowadays have multiple cores in them. And what is a core? A core is just a processor. It's got multiple processing units in there. Just historically, core was a name that Intel invented for a processor because they wanted to rebrand, because parallel processors, like I said, lost their popularities in the 95, so they had some PR company come in and tell them that core was a better name to use for it. But you can replace core with processor. You know, and then if you look a little further, you can find one with more cores. This one has 20 cores. You pay a bit more because this not only has 20 cores, but it has a lot more cache and is a little bit fancier processor. And if you want, you can buy a machine, go to the Dell website and buy a machine that has 4 of those processors with 20 cores each. So you can buy 80 cores. I think this one's actually 4 different processors, but you can put these together quite easily. And this is just a little thing of that size. You put it in a rack, and you know, has 80 cores. Well, if this one's a new one, we just bought one of these in December. This is the new Xeon Phi Knight's Landing. It's actually not, you can't buy it on Amazon yet because it's not publicly available, but you can, if you're an educator, you can go to Intel and request one, and it'll be widely available in a few months. But this one has 64 cores and 1 chip, okay, as opposed to needing multiple chips. Each of them is a full-powered Intel core. Okay, it turns out it runs at a clock rate that's about half of a regular clock rate, but they're still each full-power cores. So you can buy this. This actually only costs about $2,000, which is, you know, not tiny, but about the same as my laptop. I just paid $1,700, so it's not that much difference. Then it's not just Intel. Qualcomm has a 48 core on a single chip. Okay, so this is sort of now what you can get on a single chip is 48, 64 cores. And these are, again, they're full power cores. They're not, I'll mention graphic processing units in a minute, which are little mini cores, but these are regular cores. In fact, here's a machine with 5,000 cores. Okay, that sounds spectacular. But actually, they're just little tiny little cores. They're not general purpose processors. They're little CUDA processors. But so that's a lot of cores. Okay, and that's what a top-end, you know, graphics processing unit. You know, this one's a pretty expensive one. It's $4,000, but you can buy it on Amazon if you have that much money in your pocket. And of course, if you go to a Google, you know what these are, data centers, right? There's a Microsoft center here, a couple Google centers on here. They've got these giant rooms, basically truckloads of machines. If you go inside one of them, they look something like this. You can't really, those are racks. And they just, each one of those is a multi-core machine, and of course there's billions of them. So that's a lot of parallel processing there. And, you know, that's at the high end, a Google data center. That's obviously a multi-million-dollar facility. If we go the other direction, you can look at your iPhones or your whatever kind of phone you have. Well, the first multi-core phone was introduced in 2010. Okay, so it's not that long ago. Okay, 2 cores was a big deal. Okay, just a handful of years ago. And then, you know, a couple of years later, we went up to 4 cores. Okay, the Samsung Galaxy. A couple of years later, we went up to 8 cores. Okay, and then we went to 10 cores. And just last month, 12 cores. Okay, so that's state of the art in a phone is now 12 cores. So even phones have multiple cores. Okay, and you might say, well, why do they need them? And we'll talk about that in a minute. But so, and nowadays, unless you buy a cheap old generation phone, you're going to be hard to find, you know, certainly less than 4 cores is hard to find. And not only that, we can go even lower. Does anyone know what this is? It's a little device called, one of them is a Raspberry Pi. It's a little toy that basically you can give to high school kids, and it was invented in England, I believe. And you can basically, it costs like $68 or something like that. And it's a little computer on a chip, and you can make it do various things for you. It's a little hobby kit, and they have 4 cores. Right? It's a little $68 hobby kit is 4 cores. So the point is, even at the low end, everything is multi. And that's when I say, well, maybe not a toaster, but a Raspberry Pi, which doesn't cost much more than a toaster, has 4 cores. Now, it's interesting. We can go back and say, well, when did this start happening? I said phones didn't really happen until 2008, 10, 11, around here. But even regular processors that go in a machine, the first multi-cores didn't really appear until the sort of between 2006, 2010, we started seeing them. This is a slide from Andrew Chen, who used to be the vice president of Intel. He now left. He's now at University of Chicago. But at the time, this was a talk he gave in 2006 at Intel. I asked him for this slide. And I'm glad I asked him for it, because looking back at this slide, I realized that he was actually quite accurate in his predictions. Right? This is a prediction he was making. I think he actually gave the talk around 2007. He knew some of the next things. Larrabee actually never happened, okay, because it was too far out. But we do, so it's maybe, like I said, we don't have 100 cores on a chip now. We have more like 64. So he might have been a little bit optimistic, right? So I showed you that Intel Xeon Phi has 64. But he wasn't too far off. So he was predicting this was the way. But the point being that it wasn't that long ago that we started getting these multi-core. Right? It's a recent phenomena, and part of this talk is about how the education community hasn't really caught up yet, okay? That we're still thinking about sequential algorithms, and the machines out there are no longer sequential. Does anyone know why all of a sudden in 2006, around this time, the industry decided to move from one core to multi-cores? Or too hot. Yeah, that's exactly the reason. It's what happened is until 2000, mid-2000s, that they just kept, there's Moore's law. At the time, Moore's law meant that they increased the frequency every 2 years. In fact, Moore's law is about the number of transistors you can put on a chip. But the way that they were using those transistors was to increase the frequency by creating more pipelining, more sorts of fancy techniques for branch prediction, et cetera. And they kept increasing the, not only that, but the frequency of the processor and the amount of instructions you can finish per cycle. But all of a sudden, it became, in 2006, it became too hot, that the energy needed to power these high and high frequencies became impractical. And the only way to get more compute powers was to put more cores per chip. Okay, because it turns out that the energy that you use in a processor goes approximately up as the square of the frequency. So if you double the frequency, you make it 4 times hotter. And they said, well, maybe instead of making it doubling the frequency, we can put 2 processors on there. Okay, and then we can make it only 2 times hotter because each one takes more. And they say even better, we can put 4 processors on there and half the frequency. Okay, we've got the same processing power, and now it's half as much energy, because if you do the calculations, right? Well, in fact, we haven't increased the energy at all, right? We take 4 cores versus 1 core, half the energy, half the frequency, we put 1/4 of the energy of each core, we come back to the same as 1 core energy. So the idea here is that in order to get more compute power, we need to use multiple cores rather than increasing the frequency. And so that's why the advent of multi-cores. And you can ask, well, why do we have it on cell phones? We don't have a huge amount of computational needs on a cell phone. Well, the same observation, that power is even more important on a cell phone than it is on a laptop, because you've got limited battery life. Okay, and so they realized, well, we put multiple cores on there, we can run them at a slower clock rate. Nowadays, cell phones, actually, you have different clock rates you can run them on. And if it can run multiple cores at a slower rate, you're much better off in terms of energy usage. So if your app is written well, it's going to use a parallel algorithm to take advantage of that. And of course, then you could ask, well, where can we use parallel algorithms? Well, parallel algorithms, in some sense, are already used even before the multi-core revolution, even before 2005, on what are called, supercomputers. So parallelism existed before 2005, not in the commodity processors, not on your laptop, not on your iPhone, but it did exist in supercomputers, and they were used for solving all sorts of real-world problems. Okay, so I could just go on and on about weather prediction has been using parallel algorithms since, who knows, it's the early 90s, late 80s possible. Airplane design, I mean, nowadays, Boeing does all of its, or Airbus do all their simulations, using algorithms, all the airflow. They try to minimize the actual, physical simulations they do. They do mostly computer simulations, human genome sequencing. Of course, the sequencing of the human genome, the main success of that was because of algorithms at Celera, and they were parallel algorithms. They were highly parallel algorithms they used. And we can go on, I can't go through this whole list. And that's at the high end. At the low end, if you look at your iPhone, you say, well, what kind of things does your iPhone use parallelism for? Well, it's got all sorts of stuff it can use it. It can use it for signal processing. It can use it for the graphics on your display, encryption, compression. If you've got Siri running on there, it's got a little bit of intelligence in there. More and more we're going to see apps with vision capabilities. So you point your camera at something and it'll tell you who it is or what it is. Language understanding, again, Siri, virtual reality, computer games, all these sorts of things, things you could run on a small device and need a lot of computational power. In most cases, people have already written some parallel algorithms with these. Okay, so that's, the applications and the machines. Now we say, well, how well do parallel algorithms really work? Okay, well, there's a lot of different parallelism we can talk about, but let's sort of focus on the sorts of parallel algorithms that we teach in one of those courses I mentioned. Like in CMU, it's 210 or 451, or there were some Berkeley courses or Stanford courses. So we can look at some standard sorting, minimum spanning tree, breadth first search, removing duplicates, using hash tables, suffix sorter, some string processing, sparse, these are sort of, bread and butter of the algorithms world. And we can say, well, how much better can we get if we run these problems using parallel algorithms? Okay, and so what we actually did is we went and we took that 64-core machine, the one I showed you, the new Intel Xeon Phi, and said, well, on that machine, how much could be better? So that's just a little, like I say, it costs $2,000. It's not that expensive. It's a little thing. Chip, right? One chip. We're not talking about, a big machine of any kind. So this is a single chip machine, and we measured them. And there's two bars here. One shows the self-relative, this is 64 cores, the self-relative speed up. So that means relative to itself running on one core, and the other is relative to what we thought was the best sequential algorithm. So we went out and we looked for the very best sequential. And first of all, with this first sorting, you might say, well, why does it get better than 64 speed up? Does anyone know? It's only got 64 cores. Is what? Cache flow cache? Well, it actually turns out it's hyper-threaded. So each of the core has four threads running. And so if you write your program in a parallel way, it's only got one processor, which means it's only got like one multiply unit and one add unit, but it can sort of make use of the multiple threads by sort of interleaving, while one thread is doing the add, the other thread can go out and get some memory, and so you get some additional parallelism. But you have to write in order to get that parallelism, you have to write your algorithm to be parallel. You're not going to get anything from a sequential algorithm. And the other interesting thing here is we actually got better speed up than our parallel algorithm on one processor was faster than sequential. We're a little surprised in that is that in our parallel algorithm, it turned out some of the things we did were actually improved the sequential algorithm. That's the only case is this sort, right? And it changes. So sorting was the best. But you can see even the worst one here, which was this suffix sort here, was still about a 20-fold speed up, okay? And the average is in about 40-fold speed up. So it means you get 40-fold improvement on a little single chip device over a sequential algorithm. 40-fold is a big deal. If you go look at people optimizing code for various applications, they're getting 5-10%. In fact, if you look at any computer architecture paper, they always talk about little changes to the architecture that improve things by 3% or something. So this is a big deal, right? 40%, 40-fold. And so you say, okay, I can get 40-fold from parallel algorithm. Why aren't we teaching our students parallel algorithms, right? Okay, now, at Carnegie Mellon we are, but at most of these other places they're not, okay? So the point is, anyway, so you can get good improvements on a reasonable machine. So that was, you know, efficiency in practice. There's also a nice theory. So one success of algorithms is you can come up with a theoretical analysis. As I mentioned, it's not going to tell you an exact runtime, but it can tell you that quicksort is better than insertion sort. But the same is true in the parallel world. That there's a reasonably simple model. You can talk about, instead of in the sequential world, you talk about the number of steps or the time taken by an algorithm. In the parallel world, you talk about two measures. One is the total number of operations, which turns out to be very similar to the idea of time in sequential. So number of operations you run in an algorithm. But that doesn't tell you enough. It tells you that you know, it could be sequential, it could be parallel. You also need to know the sort of the longest chain of dependencies. So in a parallel algorithm, you got things, like I said, you can imagine the whole room working out something together. You talk to someone else, they talk to someone else. There's some chain of dependencies there, and that's what the span of an algorithm is. It represents the length of the chain. And it turns out that the ratio of these things tell you about how many processes, how many cores you can make use of. So if you divide one by the other, it tells you how parallel the algorithm is. Okay, so it's quite easy to analyze these costs. Okay, well the work is always exactly the same as the sequential work. So n log n is the time to sort. Merging takes linear time. Spanning tree takes m time, for example. But then you've got this extra cost here, which is the span, which gives you a sense of how parallel. So if this is logarithmic, if the chain of dependencies is small here, then that tells you it's an efficient parallel algorithm. Okay. So I'm not going to go in detail, but the idea here is that there is a nice theoretical cost model that you can then analyze and compare algorithms. So I might compare two algorithms which are n log n. So maybe, I don't know, quicksort or merge sort are both n log n total operations, but maybe one has a better span than the other, which would mean it's more parallel. Okay, now it turns out that quicksort and merge sort are both highly parallel, so that's fine. Okay, there's also lots of work on, well, how would you actually express parallel algorithms, right? So, you know, there's a lot of languages out there now have parallel loops, okay? So Silk is a parallel loop way to basically say Silk for it means run all these iterations in parallel. So instead of doing one and then the other, then the other, then the other, you know, iterating through, you say in parallel, take one and add it to every element of this array, okay? This form is in the G++. If you just download the latest version of the GNU C++ compiler, it's part of the standard compiler. You can just compile this. Okay, you have to put in some flag at the command line, but so what the point is, and that's only been true in the last year. In fact, it was put in last summer. Okay, so we're starting, partly driven by the fact that we have all these parallel machines. We're starting to see a lot more parallel structures appearing in different languages. Okay, Microsoft, their middle interface has parallelism built in, which means all their languages have parallel structures. So you can actually run this on any of the C# or F#. I mean, the syntax would be slightly different languages, and you can do parallel for, which means basically, this means the same as here. For every element of the array, add one to it. Okay. There's languages. Nestle was a language I worked on several years ago. They have parallelism. OpenMP is another way that you could do in C++. You could also write it this way, and you'd put this little pragma in front of it, and you'd put a command line flag when you compile it. And again, that would just work out of the box. You don't have to go find some special compiler or something that'll work for you. There's also, that's for parallel loops. You can also do fork join. There's various different forms. You can co-begin. Java has parallel built in also. Okay, so you don't, again, just a completely standard Java, and you can just say co-invoke. I think you have to load the right library or something, but and that means run these two things in parallel. This means run those and then basically wait till they're both done and then synchronize. Silk has a way to do it. We have a way that we use in our 210 class to do it that says run E1 here in parallel with this other. These are two expressions with each other. The point is there's lots of different languages that allow you to do parallelism. And furthermore, this form of sort of nested parallelism, as we call it, where you just have parallel loops and parallel fork join, is good enough for all the algorithms I showed you, all the performance numbers I showed you on the previous slides, were all written with basically just these structures, nothing more fancier, okay? It's a small white lie. We do use one additional operation, which is a compare and swap. which I don't want to go into the details to, but there's not a lot to it. So there's also been a lot of improvement in tools in the last year, again driven by this, the fact that most machines are parallel. We've seen parallel structures show up in languages, and we've seen various tools. There's now better debuggers for parallelism, although I have to say they're not yet at the same level as sequential debuggers. Okay, there's also race detectors, which is something important in parallel that we didn't have to worry about sequentially, is that in parallel, when you have two things running at the same time, they might be going to a shared resource, and depending on the ordering, you might get different results, or if they interleave in bad ways, you get different results. So this is a way to help you find bugs that are based on such results, if you get bad results. There's also better profiling tools. Again, they're not at the same level as the sequential tools, but they probably will be in the next couple of years. Okay, well, what is a parallel algorithm? I showed you ways to write loops, okay? Well, how would I actually write a parallel algorithm, just to give you a sense? Well, my claim is it's not rocket science, okay? It's actually not that hard. We teach it to our third semester students, both on the Pittsburgh campus and here, well, certainly the second year students, except when it's applied to rocket science, okay? Then it's rocket science. But so let's say, I don't know, let's say we wanted to sum an array. So we got this set of numbers, and we want to add them up. Okay, in an old sequential algorithm or in a typical course that unfortunately most places still teach, they would tell you to write a loop, keep a counter, and keep adding those numbers to that counter, right? That's not the right way to think about it in parallel. In parallel, you say, well, I can add the first two numbers. I can get 8 of you together. Pairwise, you'd each add a number. I'd end up with 4 numbers, and those were all done in parallel. And then pairwise, once more, you'd add them up. And then pairwise, and I get the 25. And the number of steps here is, well, it's the log base 2 of the number of original elements. So if I had 1 billion elements, this would take 30 steps or something, right? As opposed to 1 billion steps if you wrote it sequentially. Of course, I don't have 1 billion processes, so I'd have to be, I wouldn't get that much speed up, but this is a very parallel algorithm. And then, well, what would this look like? I mean, the code looks like something like this. I mean, I picked a particular language. This language happens to be Nestle, language I worked on, but it wouldn't look very much different in my C with Silk extensions. It basically says to sum A, if A is a size 1, this should say A0. Okay, there's a typo here, sorry. And then otherwise, I pairwise add them up, and then recursively sum the result. Okay, so this is just a way to say pairwise, add the two time i's plus 2 I plus 1 for every I in this range, and that's it. So it's easy to write this simple parallel algorithm. I mean, it's not a very complicated algorithm. And you can also work out the asymptotic cost. The total work here is n. So the total number of additions is no different than if I'd done it sequentially. If I'd done it sequentially, I've done exactly n minus 1 additions, right? I would have started with 2. I added the 1 in. That's 1, 2, 3, 4, 5, 6, 7 additions, right? This parallel algorithm does the same number. It does 4 plus 2 plus 1. Also happens to be 7. Okay, so I didn't do any more additions. I did them in a different order, and I did them in parallel. Sometimes we might do a constant factor more, but this is still a linear number of additions. So we do no more work than the sequential. And the depth of this, or the span of this computation, D here stands for the span, is logarithmic. So this is a parallel algorithm. We can do a lot more interesting things. So you can say, oh, it's sort of obvious I can add a bunch of numbers in parallel. It's not, like I said, that's certainly not rocket science. It turns out even something like this here is what I'm doing a scan does. It basically returns the sum of every prefix here. So it basically keeps a running sum. So it's like the addition, but instead of throwing away the intermediate steps, I keep them. So first I have the 2, I add in 1, I get 3, I add in 4, I get 7, I add in 2 more, I get 9, 3 more, 12, 13, 18, etc. Now this seems like a very sequential thing, right? Because I can't pairwise add them up. I have to keep all these partial sums, and it would seem like you have to do this in a loop, okay, sequential. But it turns out that this is also very easy to do in parallel, although this one requires a little different thinking, and that's why we have to sort of train our students to think differently, because if they're thinking in terms of a loop and you told them to return this, given that, return this, they're just going to write a loop to do it, completely sequential, right? And maybe that's not what we want them to do, because now they got a machine with 24 cores on it. You know, they might want to make use of those cores. Well, it turns out to do this in parallel, you can again pairwise add these up, okay? And then you can recursively solve it, okay? So you're solving on a problem that's half the size to get this result. So that's basically 3 plus 6 is 9, 9 plus 4 is 13. So I've got all the partial results here. So that's just a recursive call, okay? Now, if you look at this recursive call, I've already got half my answers. I've got my 0, I've got my 3, I've got my 9, I've got my 13. And if I want to get the other answers, all I do is I take this 0 and add it to 1. I take this 3 and add it to 2. And I take this 9 and add it to 1, 9 and add it to 5. Well, somehow I take the 0, add it to 2, right? The 3 add it to 4, right? The 9 add it to 3, I get the 12. The 13 add it to 5, I get the 18. I get them all, okay? And it's fully parallel, because I could do all these addition in parallel, and I can do all these additions with those in parallel, and I can interleave them in parallel, okay? So it does something that seems sequential in parallel, and it's not difficult. And is just showing how it's done. These are showing the arrows that show how the pieces come together. Right, I guess that's the, right. And so, so anyway, so this is a parallel thing, and we can again analyze the cost of this. You can write a recurrence, which is a typical thing we do in designing algorithms. You can figure it's a linear number of operations. It's still linear cost, and it's still logarithmic. So actually, within a constant factor, it does no more work than just that sum does. But it does something more interesting. And that's the pseudocode for it. It's not that complicated. So the point is, we can do something that's more interesting in parallel, but now we actually have to teach our students something new. But this isn't something we would teach in a sequential algorithms course, and it's probably something they would not come up with on their own with at least some help. Okay. We can write other algorithms. Here's quicksort and nestle. Now, we've all been taught that quicksort is a sequential algorithm, or we've never been told that something other than it's a sequential algorithm. Actually, quicksort's a hugely parallel algorithm. Okay, it's got a very large amount of parallelism. Well, why? Okay, just to remind you, quicksort basically takes the original data, picks a random value, finds all elements less than the data, finds the elements equal, greater. Okay, and then recursively solves the lesser ones, the greater ones, and then puts the things together. So it basically takes the recursive solution of the elements less than the pivot, a random pivot, attacks them onto the equal keys, and then tacks them onto the greater, the keys which are sorted result of the keys on the greater values. Okay. So there's parallelism here because I can make the two recursive calls in parallel. And that's at the first level of recursion. At the next level, each of those recursive calls make two more, so then I have fourfold parallelism, then eightfold at the next level. Furthermore, I get parallelism because I can compare my key to the pivot in parallel, right? Because I got this pivot, I picked a random pivot, and I could either one by one in the old-fashioned way write a loop, okay? To me, it seems so old-fashioned, writing a loop to do something like that, right? Instead, you say, let's just in parallel, and in this particular language, which again is nestle, whenever you put curly brackets, it means in parallel. So it says, for every element in my original sequence here, compare it to the pivot and pick out the ones which are less, right? And pick out the ones which are equal. So I can do all the comparisons in parallel. And we can also analyze this in terms of the work. The total work ends up being, well, it is quicksort. It does no more work than the sequential quicksort does. So it's n log n in expectation. And we can then do the depth or the span of this algorithm, okay, which is that critical path I mentioned. And you can show that it's log squared n. You can basically show that the depth of recursion is log n with high probability. And then you can show that the depth of each of these, picking the elements less than, you have to do some data movement and shuffling around, and that's log n. So the overall depth is log squared n. Okay, it doesn't matter if you fully understand this, but the point is It's a shallow algorithm. Its span or critical path is only logarithmic. And as I mentioned a little while ago, if you divide the work by the span or the depth, you get the parallelism, and the parallelism n log n. So that means with a billion elements, I could make use of about a billion over log a billion, which is 30. I don't know. We take use of about 30 million processes, which I don't have nowadays. Okay, so I don't actually need that much parallelism. Okay, so that's the just to give you a sense of what a parallel algorithm looks like. And again, it's not rocket science. In fact, a lot of the sequential algorithms we've looked at are parallel. Turns out merging can easily be done in parallel. Merge sort is trivially parallelizable. A lot of things are very easy to parallelize. So it's pretty easy, okay? And there's also a lot of you can look at, say, well, what are the techniques that we use in parallel algorithms? Some of them are exactly the same as we use in sequential algorithms. Okay, divide and conquer, as we teach all of our students, divide and conquer. Turns out divide and conquer is an inherently parallel technique. We never tell them that because we never thought about parallel algorithms. But if I divide something in two pieces and I tell you to solve one piece and someone else, well, you can do it at the same time. You don't have to wait to finish one before you start the other. There are some things which change when you go to parallelism. You do have to rethink things, so you tend to think more in terms of collections of objects, okay, which is actually not that much different than you might think if in a language like Python. So instead of thinking of loops all the time, you're thinking of applying some operation over a collection. You're saying I'm thinking of adding one element to every, adding one to every element of a collection, as opposed to writing instead of a loop which goes through one by one doing something. Like in that reduction example, you think about, well, rather than a loop that adds a bunch of numbers, well, let me think about the general notion of summing a set of numbers. So if I mathematically write a sum, using my sum notation, I equals 0, to whatever, I don't specify the order. I'm just telling you I want to add those numbers, right? You don't think about it as I have to add those numbers in some order. And a reduce is sort of like that. It's just saying I've got some collection of values. I'm just telling you to either add, and the reduce could be more than, it could take the max. It could take, in fact, any associative operation, the min, the max, the sum, the or, the and, etc. There's also, it turns out there's some other techniques which are very useful in parallel that are sometimes useful in sequential, but not as much. There's this notion of contraction. As you take a problem, in divide and conquer, you break it into multiple parts, solve them all. Okay, in contraction, you take a problem, you contract it to a problem that's about half as big, and then you solve it on that problem, just once on that problem that's half as big. So it's not dividing, I'm not dividing it into multiple pieces, I'm taking just one recursive call. It turns out the algorithm I showed you for scan is exactly this flavor. Remember my original data, I pairwise added them up, I got a problem that was half as big, I recursively solved that, and then I come back up. So the idea is that there are sort of common techniques for parallel algorithms. Some of them are the same as sequential. Some are maybe the same as sequential, but more important in parallel. But it's the same sort of notion and the same with data structures. We can come up with common data structures. So I'm just about to wrap up now. So let's just return to the original claim, which is, parallel algorithms come of age, right? And why parallel algorithms now? Okay, I'm just repeating a slide I had before, but now let's just see that I've sort of argued most of these points, right? I've shown examples, okay? So certainly I've shown you that most devices are now parallel, right? Hopefully you're all convinced about that. I've also shown you that, well, many applications, or at least I showed you a list of applications. You'll have to believe me that they can be written in parallel. Small examples were things like, encrypting on an iPhone. A large example was like weather forecasting. Simple programs and cost models. Well, I gave you some examples, which at least I think were simple. Like the summation was 2 lines of code. Quick sort was 6 or 7 lines of code. They're not that complicated. that they're efficient parallelism. We talked a little bit about, you know, asymptotic analysis of parallelism, and, you know, that sorting we can do both efficiently in terms of work and in terms of the span. And there's also some cool techniques that come up in parallelism that maybe you don't see sequentially. Reasonable tools and languages. Okay, I don't think it's 100% there yet. Like I said, it was just last summer that G++, that the GNU compiler built in the Silk primitives. Okay, so if you came here a year ago, you would have had to like go off and find a special branch, compile it yourself. Okay, or you could have used OpenMP. Actually, was available, but OpenMP doesn't do recursive calls very well, and so if you wrote your quicksort in OpenMP, it probably wouldn't have worked well. But the tools have gotten a lot better just in the last few years. Okay, so nowadays they're better. Another example is in the course 210, where we've been actually teaching parallel algorithms, which is one of the courses we teach on this campus and the Pittsburgh campus. Until this year, we were teaching parallelism, but we didn't actually have a runtime system that ran them in parallel. Okay, and just this year, the tools have gotten to the stage where we can now actually have all the students run all the algorithms in parallel. Okay, and so the tools are getting there. Okay, and some of them are there, and some of them are still being developed. I think some of the debugging tools are not perfect yet, but they're certainly getting a lot better than they were 5-10 years ago. So that's the availability of tools and languages. And the last point I was making is just that many sequential, it's not, again, this is not rocket science. Many parallel algorithms are no different than the sequential. Or the other way to say it is many sequential algorithms are already parallel if you think about it. And quicksort is a good example of that. And summation, you know, maybe you have to change it a little bit, but it's, you know, it's reasonably easy to think about how you would add a bunch of numbers in parallel. So if we go back and we look at what different universities teach, okay, we added parallel algorithms to 210 I don't know, 5-6 years ago, okay? And like I said, we've been teaching it to our sophomores ever since then, okay? And by parallelism, I mean the whole course teaches parallel algorithms from the start. It's not like we added on in some simple way. It turns out we haven't actually switched it in our more advanced algorithms, so they do mention a little bit of parallelism. These other places, they haven't got it yet, okay? Now, they have got it a little bit, so Berkeley in their 170 efficient algorithms has 2 lectures on parallelism, okay? So they decided to add a couple, touch on it. And MIT, similarly, in their design and analysis, the advanced course here, has basically a week on parallelism as well. Okay, so they both add a little bit, but they certainly not viewing it from the beginning. They sort of at the end of the course, and they say, by the way, we can run some things in parallel. And Stanford doesn't do anything because, once again, it's the weakest of the, and there's actually a couple different ways to thinking about how you could teach parallel algorithms. Okay, because I guess my point being is we're not going to get people in industry doing parallel algorithms, okay, or they're not going to be doing it very well unless we teach it. And not only that, if we're teaching this old technology, it doesn't look so good to the outside world, right? There's one way to do it, which this is the sort of the model that Berkeley and MIT do it a little bit, is they basically teach a completely standard sequential algorithm course, using exactly what they've taught for the last 40 years. And then they add, like, this block is probably too big. They probably add something that's maybe only about that big, okay? Of parallel algorithms by adding it at the end of the course and saying, oh, by the way, we can do a couple things in parallel. I think this is the wrong way, and this is part of the reason that we designed 210 in the way we did, is I don't think parallel algorithms should be different than sequential. I think when we teach quicksort, we should just tell them, well, it's got a certain work, and that's exactly what we've always told them, that it's n log n operations, and then we tell them, and oh, by the way, you can also analyze the depth or the span of this algorithm, and it's pretty small too, and so it happens it'll run nicely in parallel. And so that you don't really have to separate it. And I strongly believe that eventually we will end up at this point where we just think about algorithms without having to sort of think of them as some esoteric things that you add on at the end. So I guess that's the end. So let me just conclude. I guess I started out by saying algorithms are important. That's certainly important in every curriculum in the world, and they also have a lot of importance in practice. There's many reasons to use parallel algorithms. I guess another thing is that this happened very rapidly. And you could argue, well, why are the universities, most universities, behind on this? It's because I showed you that graph that basically there were no commodity parallel machines until 2006, right? That was when the first two-core processor showed up on the Dell website. Okay, now you could have always bought a supercomputer by going off to some special place and spending hundreds of thousands or possibly millions of dollars on one. But if you wanted to buy a commodity multi-core machine, it was 2006. That's when you could have bought two cores. And two cores weren't that interesting, right? You could argue with two cores, I have one core running my Windows and the other core, running my other process in the background. And then, cell phones we saw in 2010. It was, 7 years ago, if you were the kind of person that buys a cell phone as soon as it's announced, you could have got a two-core. Probably in practice, most of you didn't get a two-core cell phone until 2014 or something like that, right? So it's a reasonably recent phenomenon, and in some sense, we need to catch up to this phenomenon. And then, of course, part of this is, well, we need this to be better integrated. And, at CMU, we've added it to 210, but to be honest, we actually haven't added it throughout our curriculum. So we probably should have more parallelism in many of our courses. So there was the more advanced algorithms course, we don't have it. In 213, which is our Intro to Systems, we have a little bit about concurrency, but we could probably add a lot more. And there's many other courses where we could probably sort of update them to have more parallelism. But I do think we are ahead of the other universities in this respect. So that's all I have to say. And I'd love questions.
Thank you, guys.
So do you see a trend at all that we will have a similar growth in applications and that get reflected in the processes one that will ultimately consume those cores at some point where we do not need that process to run concurrently? You know what I mean? So when you explain some of these solutions, it gets to be sold as this is the only thing running. I want to take advantage of 64 cores. But if I had 64 applications running, each one is running sequentially, do I still get at that?
Yeah. So,
two, given all this potential benefit, are there ways to automate a ton of code that has been historically written sequentially into more parallelized versions in mind?
okay, so those are both good questions. So the first one is, well, could we just run multiple different jobs in some sense or more? And I think that was very much the thought in the early days when we had 2 and 4 cores. And it was a very practical way of doing it. And that, in fact, that's why I think actually there was a little lag between when the first multi-cores came on board and people actually started. Because if you've got 2 or 4 cores, you've probably got 2 or 4 things you want to run. Okay? I think that's probably not true with 64 cores. I probably think you don't have that many things different, where they all need about the same amount of throughput at the same time. Because most things, sometimes need work. If I run a top on my machine at a typical time, there's typically only 1 or 2 things which are using a lot of cycles. In terms of what we might use those cycles for is, there's also a lot more demand on cell phones for more intelligence, and I think that's where a lot of the cycles might be used. Like if I start having apps where I can put my camera and one by one recognize you all, or recognize that this is a room full of people, all sorts of those will take computational power and probably will use those cores, right? And the other part about, like I said, about the phones, et cetera, is I can make the cores have a lower clock rate and more of them, and as long as my application is parallel, then I can do that. I guess your second question was, well, can I somehow leverage existing code and convert it from being sequential to parallel. I think that's a hard task. I think there are some cases where I have embarrassingly parallel lots of things I want to run, but the effort to take sequential code and actually convert it into a single parallel code has mostly failed. That there's been a huge amount of effort. Back in the day of supercomputers, people used to say, well, can I take my code I wrote for simulating airflow and sequentially and convert it into a parallel code? And that's nearly always failed. And so really the supercomputing people have had to go and rewrite over the years their code to run in parallel. And they're ahead of the game because they've had parallelism for a while. So they've gone and a lot of it's written in sort of crusty primitive languages like MPI and stuff, but they actually have gone and rewritten that code. So I do think there will be some work in converting from sequential to parallel. Is it any other?
One more question.
Right.
In real world applications, when you're talking about algorithms running parallel, that's not an issue. There are bottlenecks, for example, I/O. How do you deal with I/O issues as bottleneck parallel work?
Well, there has been a lot of work on doing parallel I/O. So certainly if you have some sort of RAID disk system, then you can do a parallel I/O to the disk. There are other sorts of I/O where maybe you can't get it to run in parallel, but you can make it to run a lot faster, and so that you can make it less of a bottleneck. So certainly encryption nowadays, you might encrypt in parallel on your chip and then send the bits over sequentially. But if you have a very high speed, wireless connection or something, then maybe that's okay, right? But yes, these are all interesting topics that I think will have to be looked at further. Okay, I guess that's it.
Unfortunately, we've run out of sequential time.
Okay. Can we get some parallel time?
Thanks for